start now. So welcome everyone to this session of our ongoing seminar series. And today we have a talk by Professor Sasha Milov on the global analysis from the perspective of the Atlas collaboration. So this will be a 1-hour presentation followed by the question and answer session. And during the talk, if you have some questions, please put it in the chat box and we will take it up after the talk. Unless you have some very pressing questions which you would like to clarify instantly, in that case, you could raise their hand and then we could take the question straight away. But usually we'd like the questions to be at the end of the talk, we prefer. Okay, so Sasha, over to you then.
Thank you very much. Yeah, so I hope you hear me well. My slides will basically have, okay, it says that it's recording in progress. It will have numbers, so write down this number of the slide and we will continue from there. So I was asked to speak about global analysis with Atlas, but then after like 2 weeks ago, I got a very interesting mail from the organizers saying that actually, it seems there was some kind of misunderstanding, and actually, you would like me to speak about systematic and statistical uncertainty that needs to be carefully handled instead of merely presenting the results of the physics of the Atlas collaboration. Actually, I very much like this because I think this is exactly what is people are not paying attention to, and this is one of the most important things in doing analysis. So I really rethought my slides from the start, and it's not really anymore the Atlas experiment. It was not really thought to be an Atlas experiment in the very beginning, because some things which I'm going to show, well, probably are not really absolutely legal, but very close to be so. So this will be about doing the global analysis using Atlas as an example. Since we are going to speak about uncertainties, let's define what the uncertainties are. Uncertainties are estimators of how far the measured value lies from the true one. And it's like shockingly amazing to me that back in the 70s, many papers in high energy physics wouldn't even discuss the uncertainty. Here is the example of that, right? The guy was measuring, reporting like 0.28 particles, actually charged particles, I forgot to mention it, per unit of rapidity as a function of log scale S. Right? Today, that's not possible. Today, there will be plus minus something, and that will be a result. For modern results, the measurements and even experiments are designed, built, and optimized to minimize the uncertainties of the measurement. Uncertainties is the central part and sometimes the most important and even time-consuming part in working out the analysis for the publications. So, since it's somehow it isn't okay. Yes, first of all, let me say one thing at the very beginning. Uncertainties are not errors. Please do not call uncertainties the errors. These are very different things. Sometimes and very often you will read in the captions to the figures, error bars on experimental points indicate the statistical uncertainty. That's absolutely correct. But if you ever read the bars on experimental points indicate the statistical error, that's a catastrophe. It means that you have to call the editor and ask to publish the erratum on your paper. Please don't call uncertainties the errors. These are very different things. The meaning of the error bar. So when you plot the error bar on the graph, like it's shown in the red on the left, right? What you actually do by convention, it's not necessarily that you have it in mind, and you can redefine it, but unless you do it explicitly, you plot by convention the size of the RMS of the distribution, which supposedly be Gaussian, from the measured point to the true value, right? And since it's a Gaussian distribution, then 68% of your statistics supposed to sit within the error bar, right? And of course, 30% supposed to sit outside. And this is only a convention, but unless you do something else, this convention holds. And sometimes people run in all sorts of like funny mistakes looking at their own graph. Like, for example, on a graph like this, there is a clear mistake. And I will give you 10 seconds before I go to the next slide to figure out what it is. The error bar should be touching the true value, and fit is a representation of true value only in 68% of cases. That means that if I'm plotting here 30 points, then 10 of them should not be touching. And 2 of them not touching means that my errors are wrong. It means that I did something wrong in my analysis by calculating my error bars incorrectly. And this is equivalently bad mistake as to just making them too small. The large systematic uncertainties or statistical uncertainties, in this case, these are more like statistical uncertainties, should be corresponding to the convention, unless, of course, you redefine. Since we are speaking about bad plots, that's an example of another bad plots, because your markers swallow the statistical uncertainties. This is just a way of presenting your data in a bad way, and in many papers, you will actually see the case when the statistical uncertainties or some kind of uncertainty is smaller than the error bar, than the size of the markers. But to me, it's just a bad plotmanship. And if you have a way to avoid it, my suggestion is to avoid it, because showing that without statistical uncertainties is not the correct way to do it. Okay, so let's speak a little bit about some customs and heritages, because we already started speaking about customs. This is the title of the Atlas paper, and there you will see like systematic and statistical uncertainty, which I'm showing here in blue, the systematic uncertainty that are coming from Atlas Detector and limitations of the analysis procedure. Then you will have like luminosity uncertainty, which in principle is also the systematic uncertainty, is just shown separately because it belongs not so much to Atlas, it belongs probably to LHC or to other subset of the detectors, which are used to work out these results. You will have the model expectation. The model expectation basically is a separate value here, but in some cases it can be also a part of the measurement if the measurement uses the model expectation, the model to get to the results. And there is also the background expectation. And honestly, I don't even know why it's shown here as a separate thing. I'm probably an author on this paper, but I never come to work on these particular results. Anyway, it happens. Let me try to make a little order of my own, the way I understand it. So a long time ago, on an experiment called Phoenix, people said a very interesting thing, and I still really very much like it. They say there are no such thing as statistical or systematic uncertainties. There are 3 different types of uncertainties. Uncertainty of type A is the uncertainty which is uncorrelated point by point. So if you look at the right-hand side, that's an illustration. So each point, which is red, can go with respect to the black point the way it likes, up or down. Type C is a fully correlated scaling uncertainty. It means that if you look at the bottom, then there are points which are going either all down, like in the example, they can go all up because it's a scaling uncertainty. And then there is B, which is somewhat correlated point by point. To be honest, they put on B everything they don't know about A and C. But if you really think about what is behind this definition, you can think of them in terms of kind of like imaginary Fourier transform. It means that every uncertainty, every source of your systematic uncertainty has kind of a generating frequency. If this generating frequency is higher than the inverse distance between the points, like I'm showing it here with D, then the frequency is so much that it will pull each point independent from its neighboring point. And it will be resulting in the uncertainty of type A, like here. If you have this underlying process, which is very slow in terms of frequencies, such that it can only rise all the points up or lower all the points down, then it will be the systematic uncertainty of type C. And if it's somewhere in between, it will be of type B. Again, as I said, it's not always easy to figure out what the uncertainty frequency is, but sometimes it helps you first to model the uncertainty And second, at least to separate certain of them, thinking of their generating mechanism. To me, it's a better way than calling them statistical and systematics. Let me show how it works. So if you take a Phoenix plot, like is shown on the right here, then systematic uncertainties of type A are the error bars. They combine, of course, the statistical uncertainties, which are by definition the type A uncertainty, but you may have also systematic uncertainties, which are also type A. Then you may have C uncertainty, which Phoenix likes to plot on the x-axis, on the axis around 1, of course, when we are talking about nuclear modification factor. Okay, so you have all this bunch of different systematic uncertainties depending relating to the different curves, and then the systematic uncertainty class B or type B is shown here with the squares. Interestingly, that other experiments like Alice sometimes does the same, and probably the systematic uncertainty of type C is the same systematic uncertainty of type C, but everything else related to boxes, you should ask the authors of the paper. There is something which I said explicitly, and maybe you sort of like agreed to me, but you did not really think of it the same way. It's kind of a philosophical question. Coming to the statement about the uncertainty B, you don't really know what they are. And this is actually very true because no experiment is ideal. No measurement is possible without loss of information. You think that you measure everything, but you measure only a part of it. Doing physics analysis basically is correcting for those losses. And every correction is based on an assumption. You have to make certain assumption which will allow you to correct back for your missing information. For example, you think that you know what is the efficiency of your detector. That's an assumption, because after all, it's based on a certain Monte Carlo, and your Monte Carlo can be different from truth. If you want to know the uncertainty, if you would know the uncertainty on your correction, you would do it as a part of the correction, right? Because if you actually know exactly what it should be, then you just incorporate it in the correction and do a better analysis, right? So the uncertainty is the part of the correction which you actually do not know how to do. And for that reason, the systematic uncertainty cannot be precise. If you would say that we are doing science and the measurement is a part of science, then systematic uncertainties are somewhere between science and art. Sometimes you have to play tricks and do some extra assumptions in order to estimate the uncertainties, which you by definition cannot know. And this is actually a thing which will be inside several things which I will be showing you in the following slides. So it's supposed to be Atlas, and this is the Atlas paper which went on the archive actually last month. It's a very new analysis, and it's absolutely global, because what can be more global than measuring the nuclear modification factor? This is the analysis which is kind of schematically shown here. From raw data to the result, you use the Monte Carlo to do different things. You select your events and you select your tracks and events. Of course, this is the charge particle array, right? I mean, this is the measurement of the charge particle array, which is, again, a very global and classical heavy ion analysis. You select your events, you select tracks in those events, and then you correct for losses. It's in fact a little bit more complicated than that, because in every step you have different things you have to care about: the detector stability, centrality, the triggers, the quality, the vertex, particle definition. I wouldn't be able to go through all of them, but every step in this analysis actually will come with this systematic uncertainty. Let me show you a few basic things. Okay, so this is the part of the detector which is involved actually in this measurement. Okay, this is what is called the inner detector tracking system of the Atlas, and it consists of 3 subsystems. So the interaction region is somewhere inside the beam pipe, which is shown here. Then there are 4 layers. It's the old picture now. We have 4 layers of the silicon pixel detector, which is shown here. And then you have the silicon tracker, semiconductor tracker, which is shown here, and then the TRT. Well, a TRT we can forget about because it's a straw tube detector, and in heavy ion collisions is absolutely saturated by the number of particles which we have. Then you can do a very simple estimate. You can take a 100 GeV particle with which needs to fly to the end of the last detector about half a meter, which is shown here, right? This is the end of the SET, in 2 Tesla magnetic field, and you can calculate it will be deflected by 250 microns, roughly speaking, which is absolutely measurable with silicon detectors. So you can do a measurement up to the range of, let's say, about 100 GeV. And if your detector is, let's say, thin enough, such that the multiple scattering for this particle, electromagnetic multiple scattering of this particle, is not really killing your measurement entirely, which is the case of Atlas, you can actually measure to 100 GeV tracks. But then the question is, what is going to be your problem? And your problem will be different at different stages and different intervals of your momentum. At low PT, it will be the occupancy in your channels. Why I'm saying so? Because to reconstruct the low PT track, you need to open it's like in the tracking model, you need to open the corridor where you search for the hits on these tracks. And once you are in the low momentum, you have to open it wide enough in order not to lose the hits on the track, which is significantly bended. The cure about this kind of problems are the quality cuts on the tracks. If you go a little high in momentum, let's say 10 GeV, of course, the borders are relatively arbitrary, then your biggest problem is not going to be occupancy anymore, it will be secondaries. Because certain particles decay in flight, and if you have enough of those particles, they will be looking back, they will be looking to you as the primary particles, but they are not primary particles. The tool to deal with such kind of problem is track-to-vertex matching cuts. And then you go to very, very high PT, you will be ruined by essentially hadronic interaction of your particles with the rest of the material in Atlas. And in order to avoid this problem, you will be looking only in the regions where you have jets, because high PT particles are only coming with jets, and you will not be looking at the particles which are presumably coming from electroweak boson decays. So that complicates your analysis a lot, but the way it works can be illustrated with this plot. So on the x-axis is the momentum of the particle, on the y-axis is the accuracy of matching the particle to the vertex. So if you take, of course, I mean, the good particles should be properly matched, and this is shown with the Monte Carlo, which is yellow here. And then you pull all the particles out of the box, which are reconstructed by Atlas experiment, you will have this green line. You apply the tracking cuts, and it helps you, especially at low PT. It doesn't look that much, but it's a log scale, so you have lots of particles here. There are many more particles here than at the tails. And then you jump from green to blue. Then you ask the particles to be matched to the vertex, and you drop to red. And basically, only at the very beginning, at the very high PT, you will be matching them to jets and removing electroweak bosons to actually get to the black particles. This is the basics of the analysis. Now, where comes the systematic uncertainties? Unlike the guy who was publishing this paper in '77, who forgot to mention that he is actually looking at the charged particles and not at all particles in the event, Atlas is very peculiar about that. Atlas wants you to define, or wants us as the analyzer to define what we call the charged primary particle. And the definition actually is given here. This is an excerption from the paper, which says that particles with a mean lifetime greater than 0.3 10 to minus 10 seconds. And the funny thing, if you look at what particle has this lifetime, you will see that it sits right below the sigma baryon. So what is so peculiar about this number or the sigma baryon? The answer is very simple. This lifetime is, if you multiply it by the speed of light, is about this half a meter that the particle should go through the detector. And the problem is the following. So if particle has low momentum and immediately decays, let's say at the pixel detector, you will not see it. But if the particle has enough momentum and will reach in the end of the detector, then you'll trace it because sigma baryon is a charged baryon, right? And by definition, it counts as the charged primary particle. Now, of course, you can try to cheat the nature and say, well, maybe I choose another definition. Maybe I exclude sigma baryon from my primary particles and move my cut from 10 to minus 10 to 10 to minus 9. Okay? Not going to work. Because doing this, you're redefining the problem. You're not really solving it. The way to solve this problem, and this is not easy in Atlas at all, is to look at the Alice experiment. Because we, in the Atlas experiment, cannot do the particle identification. In very rare cases, at low PT, we can say that this was a proton and this was a pion. But when it comes to sigma baryon, it's basically impossible. So we take the information from the Alice experiment, and we are trying to calculate what our efficiency should be when we are doing this with a proper particle composition. You can see this set of absolutely crazy curves, which are based on the Alice results, which are incorporated in these analyses. And you can see that they have a peculiar place here at around like 5, 6, 7 GeV, where the particle compositions start to like jumping above, showing this like bulging. And if you look at the final results of Atlas, which is the track reconstruction efficiency, you can say how much we actually paid in our systematic uncertainties in this region for the fact that we do not know the particle composition. This actually doesn't look very nice, but this is the honest way to compensate for something which we do not know in the analysis. As I was saying, every correction for the track reconstruction efficiency should be coming with an assumption. And if we cannot measure something inside the Atlas experiment, we prefer to make our systematic uncertainties larger in this region in order to be honest in the final results. Now, okay, so this was an illustration, but it's actually is showing you how the systematic uncertainties show themselves in the final result. What you probably don't know, or I will show you that in a moment, is how we define the reconstruction efficiency. And actually, I have a definition here, and to the first glance, it can look to you absolutely crazy. The efficiency of the measurement actually is worked from the Monte Carlo. So we take the Monte Carlo, the generated particles, we plot them as a function of PT or eta or something else, doesn't matter. And we ask which of those particles have a matching to the reconstructed object. And then we divide it all by the total number of particles which we generate. It looks a little weird, but it actually makes a lot of sense. Let's go to this schematics, which I was putting at the beginning, how we go from the raw data to the results. And on the path there, we select the tracks. We select the tracks, and inside this selection, we want to remove those tracks, which are fake tracks, which are not really real particles or secondary particles, something which we want to remove. Fake tracks can only exist in the reconstructed sample. Fake tracks don't come from generation, from generators. They always are built inside the tracking system of Atlas. So if you want to remove them, you have to do it at the level of reconstructed tracks. Then, after you did that, you take those reconstructed tracks and you correct for the mismeasured momentum. For that, we use the procedure which is called unfolding. So you build the transfer matrix, which an example is given here. On the x-axis, you have reconstructed PT. On the y-axis, you have the generated PT. And you see that it has a width. And this width is defined by the resolution of the tracking system. And then we transfer our reconstructed tracks, give them momentum of the generated particles. And only then we correct for losses. Because in this case, the generated matched the reconstruction of regenerated sort of sits in the same domain. Inexplicitly, I'm telling you that reconstructed tracks and generated particles are very different objects. And if you want to do your analysis right, and I will show you in a moment why, you have to keep them apart. Why is it so? This is basically the cross-section of this matrix. The R, which is on the x-axis here, is reconstructed momentum divided by generated momentum, -1, to center it at 0. So basically, all the particles are sitting here, right, in this peak. It means that their momentum, reconstructed momentum, is close to their generated momentum, which is a good situation. And sometimes you may have a particle which reconstructed momentum is very far away. Let's say it's different by a factor of 2. Okay, you may still want to count this particle as reconstructed. But in principle, I can push the argument to the edge and say, what if it's different by a factor of 3? What is it different by a factor of 10? Would you even call this particle to be reconstructed? And the answer is, actually, it's up to you. It's up to you what you want to call the reconstructed particle. Because at the end of the day, you would need to find out which systematic uncertainty is easier for you, the systematic uncertainty on efficiency or the systematic uncertainty on unfolding. Because if you count this particle to be reconstructed, then you need to unfold them. If you want to cut, then you need to compensate for the losses. And the answer is, really, you need to think how you do your analysis. I don't have an answer to that. Something which is very special, is actually a sanctum sanctorum of heavy ion physics, centrality. Centrality, I think I don't need to explain what centrality is in this forum. I hope that you know. If not, then ask me later. But basically, the centrality is something which each experiment does independently, and then compare the result between each other. That's a little bit funny. In some cases, they agree pretty well. In some cases, and I know in which I think that we have real troubles between experiments and understanding centrality. As an illustration, I can tell you that when it comes to proton-lead collisions, not to lead-lead collisions, which I'm going to speak about, but to proton-lead collisions, the 3 different experiments have absolutely different approaches. Atlas is trying to do centrality in P-lead. CMS doesn't do any measurement which involves centrality in P-lead. Alice measures everything as a function of n charge, pretending that centrality doesn't exist. Okay, I understand all 3 choices, but here I'm going to speak about the lead-lead collisions. In lead-lead collisions, you have, and you always start with the Glauber model, which in fact may be simple, but it's very, very precise. Because the basics of the Glauber model, now we have version 3.2 or something like that. The core of the Glauber model is the Wood-Saxon distribution, which really measured distribution of charges in the protons with the radius of the proton, with the cross sections. Everything is actually pretty well defined. We also know what the neutron skins are. So when you run the Glauber model, no matter how sorry, a little bit lost my thought. This distribution will be actually very precise. It will be actually very precise also for n collisions. And in case you have some deviations, they're well controlled within the systematics of the Glauber model. You take this distribution, you assume certain particle production, and you put it on the detector response. The detector response is shown on the right. In this case, it's Atlas, so it will be the forward colorimeter sum of the transverse energy. If it would be Alice, I think that they're using some heat detectors, right? I forgot what is it called, but basically there's a number of heats in the detector. In both cases, it's very precise, especially if you think about Atlas. Yeah, it's hadronic colorimeters. Hadronic colorimeters are not very precise, but once you have like a 4 TeV in the forward energy, which means like 100 TeV total energy, colorimeters are very precise. So the shape of this curve is very well defined. What is sitting in between is the assumption about the particle and charge or the energy production in the heavy ion collisions. That is not really precise, and the problem you can see immediately, because if you take this point here, which is 4 TeV, right, and you divide by 400 divide by 2 number of participant pairs, you will have like 20-25 GeV per participant pair. If you measure the same in the proton-proton collisions, you will have half of that. So it's very clear that the particle production changes as you move from peripheral collisions to central, and we know that as a result of our measurements. So what is used instead of the true particle production is the so-called 2-component model. Well, two-component model basically says that the particle production or the energy production in the final state is some kind, it has two contributions, one from the number of participants and participant pairs, and the other is from the number of collisions. And the balancing factor between them is this parameter x, which is found from the fit. Seems like it's not very precise, but the truth is that it actually doesn't matter. Because when you think about what defines your fit, and the fit is shown here as red, sitting on top of the black, which is the measurement, sorry, opposite. I think that maybe the red is the measurement and the black is the fit. The thing actually is not about accuracy or the precision of the Glauber model. If you are trying to fit something in this region, you can fit anything you want, because basically the two curves are so much alike, this curve with a detector response, that you will succeed in the fit even if you have a very wrong model. In this region, you will also succeed because there are, first of all, this model, it's already fails there, and this is too far away when you want to work out the number of participants in peripheral collisions here. But here you have a very different problem. Here you have a problem in which you do not know what is your mean bias event composition. When you go to LHC energies, when you go to collisions at 5 TeV, you basically have different physics processes. And I mean, first of all, photonuclear, but when you come to P-light, it can be also diffractive, which actually start contributing to this region, right? And therefore, you cannot really fit the first several points. You have to step up to 80–90% of your centrality and only fit above that. And there, as I said, you can fit anything you want, because these fits are not really precise anymore once you are in this region. You're like fitting two functions which are very much alike each other, right? And trying to find the transformation parameter. As a matter of fact, when you're speaking about centralities, you will always pay in the peripheral collision. And this is one of the examples, right? This is what is shown here. Once you get to the central collisions, everything is fantastically precise. Once you go to peripheral collisions, your error bars start to be blown up. And if you look in the paper, they are absolutely driven by centrality determination. What to do? Well, first of all, you need to understand your composition. And first of all, for that, you need to understand the photonuclear collisions. One way of amending the situation is the 0-degree calorimeter, which is built now by CMS and Atlas as a joint project, because 0-degree calorimeter is somewhat sensitive, sorry, not somewhat sensitive, is the tool which can distinguish between photonuclear collisions and hadronic collisions. You can calibrate your centrality with electroweak bosons. This is something we did. Or you can simply use the charge as Alice does. Also, this is a good approach. So when you put all things together, this is from the internal node, basically, which I'm not supposed to show, but this exactly follows every step of your analysis. Select events, uncertainties on the track to particle association, uncertainty on the track quality, it sits somewhere in this region. Corrections, they're sitting in this region, and then the centrality and luminosity determination. This is exactly the same idea. Every correction step into your analysis is based on assumption, and therefore it comes with its own uncertainty. So, what can you do with an uncertainty? Actually, the answer is redundancy. This is something which actually helps you with systematic uncertainty. It sounds a little bit funny, but let me explain what I mean. Redundancy can be of all different levels. Redundancy in the physics principle. Good detector is the detector with redundant subsystems. It means that you can measure the same thing in more than one channel. Redundancy at the level of the detector design and measurement technology. Good measurement, more than one measurement of the same value. Redundancy at the level of algorithms. Try to find a different way how you can measure the same thing. Redundancy at the level of data sample. The more statistics, the better the systematics. Somebody can tell you that statistical error has nothing to do with the systematic uncertainty. That's wrong. Actually, systematic uncertainties can be improved if you play right things with enough statistics. Redundancy at a human level. In some cases, people do the blind analysis, not to be able to look at the data till the very last end and then just appreciate the result they worked out without looking at them. But as an example, I put this table here where you can see basically big colliders, not so big colliders, doesn't matter. The colliders which were actually working in time of modern physics, and strangely, each of them have at least 2 experiments. It's very unusual that you will have a collider with only 1 experiment, and I don't want to comment why. I think you understand why. Let's go back to the examples which we already studied. So this is the atlas in the detector tracking system, which has at least 3 subsystems, but this subsystem is not really very workable in the heavy ion collisions. But pixel detector and SCT, pixel detector has 4 layers now, right? And SCT detector, they are. And basically, you can build a track here, you can build a track here, and you can recalibrate one track for another track. And this is what people do when we have detectors like this. I will show you a slightly different example, how we do it in the analysis. Of course, I will say redundant detector is a good idea if you come to the funding agency and want to, and you will tell that you want to build a redundant detector. It's probably not a very good idea. But the redundancy in this example is coming naturally because more than one subsystem is needed to actually do a proper tracking. Here is the algorithmic redundancy example. This is an actual measurement which we did in Atlas for measuring the charge particle multiplicity without breaking it into the PT spectrum. And basically, if you want to do something like that, you really want to sit as close to the vertex as possible, because then you don't care about event composition. You don't care so much about correcting for the missing PT region, because some tracks would actually never reach the detector due to the magnetic field. So what we did, we actually used the innermost layer as the indicator of charge particle. We actually counted only this hit, the first hit in the detector. And we said, if there is the first hit in the detector, we count it essentially as a hit in method 1 and 2. Method 1 then said, if I have in a certain window at least one hit, I will count the first hit. Okay? Basically, these hits which are following, they will the confirmation of the hit in the innermost detector. Method 2 said, well, if I have one hit, I have one confirmation. If I have 2 hits, I have 2 confirmations. If I have 3 hits, and so on and so on. Means that we allowed more than one track going for the first hit. And then, of course, we run immediately in the problem of just double counting, right? In order to avoid this double counting, in order to avoid the just random associations, we did the following thing. Instead of looking at this part of the detector, we looked at the detector which was 180 degrees to it, okay? And if we would find a hit there, we will sort of subtract it from this matching, right? And then there was a method 3, which was essentially building the tracks as they are with all the machine learning algorithm, with all the things, just in the short 3 layers of the pixel detector. Actually, it worked. So this is method 3, which was with real tracks, and it has less efficiency. So it has more to correct for based on the Monte Carlo, right? Because if you want really a confirmation in the 3rd layer, then, okay, you're losing certain amount of tracks. Then there was method 1 and 2. Method 1 was more efficient at the edges. Method 2 was less efficient at the edges, but more robust here. And then we all corrected them to get the final results. And then we compared them, and we saw that they disagreed to 2%. And this 2% was legitimately going on systematic straightforward, right? The only thing is, what kind of systematics we are covering? Because you have to be very careful when you did something like that, and you can say, oh, I did the systematic of my measurement. Not at all. You did a systematic on a very peculiar step mu measurement. You did a systematic only on the fake and secondary production and on a limited knowledge of your momentum distribution of your particles, which in this case, we didn't know where to take from because the measurement was not paying attention to the PT distributions, okay? So it's a very good example of doing different methods, measuring the same things in different methods, but you have to be very careful about which part of the systematic you are actually covering with doing that. Well, this is basically a classical example of the redundant physics principle. It's not a global measurement anymore, though it has a very direct connection to the global measurements. It's a verification of the Glauber model, which is actually in the right plot here. But the essence is the Z boson. Z boson is a classical example for the Glauber model because Z boson itself does not interact hadronically. If you measure the Z bosons, you essentially calibrate the nuclear thickness function. But the beauty is that Atlas is capable of measuring Z's in dimuon channel and dielectron channel. And of course, when you measure both, then you can compare the results. And you can improve your systematic in a drastic way, which is shown in the right-hand side plot. But I want to show you something else, a lot more elaborate case, measuring the same in the proton-lead collisions. Let me explain what I mean. To measure electron or to measure Z boson, of course, you need the dimuon pair or dielectron pair. To make a muon for the muon pair, you have to find the muon in the tracking system of Atlas and in the muon system of Atlas. So when you're finding a muon in the muon and track system, you have good muons. Likewise, if you want to find good electrons, you are finding them in the tracking system in the colorimetry. Okay, in the colorimetric system. And then you have a good electron, or two good electrons build you the Z boson. But the most interesting measurement when it comes to PLED is at the high rapidity. And at the high rapidity, muons don't work and tracking doesn't work. Only colorimeter can work. Because colorimeter in Atlas extends to 5 units of pseudo rapidity. In this region, you can have a cluster in the colorimeter, but you would never know whether this cluster is an electron or a photon. Nevertheless, you can do your best. We measure dimuons, and this is the dimuon mass peak exactly at the place where the Z boson should be. This is dielectron mass peak, exactly where it should be. And this is something very exotic. One electron is really a good electron, like here, in the tracking system in the colorimeter, and the second electron is just a cluster in the colorimeter in this region. We are not asking it to be confirmed by the track. We are just looking at the region where a tracking system doesn't work anymore because it doesn't exist there. But the colorimeter is still there and it can give you a cluster. And then we combine the two measurements, the Z to mu mu, which is shown here in the right-hand side, with really small systematics, and Z to E with larger systematics than the Z to mu mu, but also with 2 additional points on the right and 2 additional points on the left. Now we can we see that where they overlap, actually the results look reasonable, and then we can try to combine them almost the same way as we combined them before, like this. In principle, unless I will tell you, you would not be able to, you would probably miss this. But you can see that the resulting systematic uncertainty after combining electrons with muons is different from the systematic uncertainty of only electrons. And you can ask, how is that possible if there is no muon result in this region? And this is really an exotic example of how you can handle your systematic uncertainty in a way which was sometimes proposed by Phoenix. The thing is that the systematic uncertainties can be of 3 different types. And if you isolate the type C systematic uncertainty in the entire region, you can ask yourself, what is the contribution of the systematic uncertainty of type C for these 2 points? And you can know it because it's a scaling factor. Okay? In which case, you can say, well, I have a much better measurement from the muons why should I use the systematic uncertainty type C from electrons? I can substitute it with the systematic uncertainties of muons because it's just a scaling factor. And in this case, if you think of the systematic uncertainties, really break them down in the components, you will be actually able to improve your results even in the place where you don't have the second measurement. And this is what was done. So these 2 points actually moved and the systematic uncertainty squeezed because we actually did this full full study of the systematic uncertainties in the central region and then propagated them to the forward regions. Which comes to another very interesting thing which you can do with redundant detectors. I will explain how that relates to the previous example. The so-called tag and probe method. Let's take some well-known physics process, like J psi decay into mu mu, or phi decay into kk, or gamma conversions, and reconstruct it only with a part of the detector. Of course, the detector has to be redundant. It has to allow you a measurement of something. Like in the previous example, we took the Z2EE and we reconstructed the second electron only as a cluster in the colorimeter. So the first electron was fully reconstructed with the tracking system and with the colorimeter, but the second electron was reconstructed only in the colorimeter. Let's call it subsystem 2. Then we looked at the invariant mass peak, right? It was really nice. It was wider than other peaks, but no question that this is a Z-boson. And basically, if you take from here to here, right, you can absolutely say that it was an electron which formed the cluster. Now, we did it outside the tracking system, but we can do it also inside the tracking system. And if we do it inside the tracking system, we can tell there was an electron in this place. Now, find it. And this gives me an ability to actually measure the efficiency of the tracking system from the data itself. And not only tracking system, the trigger system as well. And then I can, play the other game. I can find it in the tracking system and ask the colorimeter what was its energy measurement. Or I can do it with muons and ask the muon system to trace me back to the tracking system for a muon, or take the tracking system and trace it to the muon system the opposite way. This is called the tag and probe method. The tag is something which is very well defined. It's the first electron, which is very well measured. It has to be a very high quality electron. Then it should be a constraint on the process, J psi, phi, gamma conversion, or something else. And then the second electron essentially is a probe, which can find out what is the efficiency or the resolution of the system. In principle, at this moment, I can forget about the Monte Carlo, right? Because I have a very good way to measure it directly from the data. And this is exactly what we do not do. We still use the Monte Carlo for 2 different reasons. First of all, maybe in a particular case, you can be without Monte Carlo, but in most of cases, you would not be able. So first of all, it's much better to make the Monte Carlo better rather than just stay entirely without it. The second reason is that no matter what you do, data has biases. You will, for example, if you would try to do it with J psi, at some moment you will go to very high PT, and muons from J psi will be too close to each other, and you wouldn't be able to calibrate the trigger because it will be always self-firing. For that reason, it's much better to actually do what is called the scale factor. You do this tag and probe method in the data, you do the tag probe method in the Monte Carlo, and then you compare the result, in which case you are more unbiased rather than just pulling it from the data. Advantages: data has biases, it's very difficult to get rid of them. And then what I said about the Monte Carlo, that you have to use in a much broader sense than just for a particular measurement in a particular PT region. Nevertheless, the tag and probe method is a very, very powerful tool which allows you to improve your systematic uncertainties for many measurements, not only for Z-boson and J-psi, for many, many measurements which you do, and it really like uses the redundancy in the detector in a very, very good way. What I would like you to take away. In modern physics, the uncertainties are essential, and sometimes the most important and the most time-consuming part of the measurement. Some old conventions about uncertainties always don't work or not really effective. Breaking uncertainty into statistical and systematical is, to my view, is a little artificial. The real question is the correlations between the uncertainties. Uncertainties are generated at every step of your analysis, except for drinking coffee, of course, but then depends how much you drink. There are no such thing as let's neglect this uncertainty. And don't even try to write it in the paper. There is let's estimate this uncertainty and show that it's much smaller than others, then you can neglect it. But the real thing is that you're not neglecting anything. You are really studying them and then you are neglecting it. The real tool to suppress the uncertainty is to do the measurement in another independent way. This is what I meant by redundancy, because redundancy of your apparatus, method, algorithms may help you in that. But in principle, this is try to do it in another way. This is what really gives you a handle on systematics. Working on the uncertainties, that's my sort of thinking about that working on the uncertainties, the main difficulties in working on the uncertainty is not to cheat yourself. You think that you measured an uncertainty in the other way, but in fact, you're measuring only a small tip of the uncertainties. You're measuring only one step in your analysis, not all steps in your analysis. So you need to go back and think really in which place of the uncertainties you are doing an improvement. This is almost the end of my talk, except that I want to show you one more slide. It's about presenting experimental uncertainties. So we have our physics Bible. It's called particle data group, right? And typically everything which is written in the particle data group is very transparent, very concise, and very up to the point. Except for one thing, if you ever try to read how they do the systematic uncertainties. Let me read it for you. I will start from red, which is more clear, and then go back to blue. In all cases, the central value, so the result which you publish, should be given with a precision that is the precision of the systematic uncertainty. Okay, that's easy. Now going back to the systematic uncertainties itself. If the three highest order digits of the error lie between 100 and 354, remember this number, we round two significant digits. If they lie between 355 and 949, we round to one significant digit. Finally, if they lie between 950 and 999, we round to 1,000 and keep two significant digits. Honestly, if you ask me what's the rationale behind doing that, and I was investigating for the last several hours, it's so-called round to the nearest 10 rule. But in fact, I'm not sure that I will be able to prove you these whole numbers. But on the left, I have put you sort of like a table which explains what they want to say. If your number is in the green region from 10 to, let's say, 335.4, right? It's actually means that the digit of 3 is close to digit of 1. I mean, it's the value which they care about. You should think about that yourself because I don't have a proper language to explain it. So the digit is like small enough so that you need 2 digits to actually explain your uncertainty. Once you're above this interesting number, 354, you actually have, it's enough to have 1 digit because this digit is much different from, it's already like 4 times different from 1, and you have enough precision in this number to actually show what your systematic uncertainty is. And then, of course, it goes in cycles. I don't understand why they need this small thing with 2 or 3, but it's really concerns a very, very short region of data. The interesting thing that Atlas and many other experiments follow this convention. I was like highlighting the same abstract that I was showing you before, except for 1 digit, which of course is 4.1. They didn't round it to 4. because the 2 is the compensating, is the other number here. But in all other digits, Atlas follows this rule, though Atlas, I know it from within, they have their own rounding rules. Basically, the essence of what they're trying to say with this cooking recipe is the following. Don't pretend that you know uncertainty better than you can, and don't pretend that you know the result better than your uncertainty. This is the essence of what they're trying to say with this rounding rule. And actually, if you ever publish your paper or write your thesis, I believe it's a good idea to follow. At this moment, this is it. Thank you.
Thanks, Sasha, for this very nice talk. So this talk is now open for questions. So please feel free to unmute and ask your question. If you have, yeah, I have see a hand, Rishi.
Yeah. So one question I had was with the discussion about centrality. So Atlas measures centrality as you should by using sigma ET. So this is the forward calorimeter. But the N charge distribution is related to N colon in part. This is the N charge.
This is in charge for. This is in charge for in terms of Alice. So Alice will do some kind of number of heats, which essentially is the number of charged particles still in the forward. But again, if you think about the transverse energy and number of charged particles, I would recommend you the old Phoenix paper. I think that was remeasured then by Alice, that essentially the rule of thumb is 1 GeV per particle. I mean, if you just measure the total energy in the calorimeter and you measure the total number of charged particles, they scale with each other pretty straightforward. It really doesn't matter what you measure.
Oh, I see.
Phoenix, if I remember correctly, was using beam counter, which was a Cherenkov detector, and it was measuring some crazy mixture of charged particles and converted photons, which coming from pions again to define their centrality. The essence is forward. You want really have lesser jets there and decouple what you do in the central region. But whether it's going to be number of charged particles or number of ET or number of something else, any activity, let's call it activity.
Okay. Okay, and I had one more question. Since you mentioned about jets being measured from the charged particles, so this is one thing that we think about a little bit. So it's easier to calculate observables where you think about fully reconstructed jets, right? So like charged and uncharged particles both. And now the question is so does Atlas have any analysis which connects the charged particle jets with the fully reconstructed jets, or one just has to do Monte Carlo to make that connection? There's no other way to make that connection.
Okay, so now you are putting me in historical trouble between Brian Coe and Peter Jacobs.
Okay.
Let's put it this way. I think that there might be some analysis in Atlas which is dealing with the charged particle tracks, charge reconstructed. Sorry, with the track-based jets, but it's like I have a little problem. First of all, I'm not doing this. Okay, so I'm trying to stay away from jets, not because I hate them, it's because I'm doing something else. But I think no. Well, I don't want to say. I think jets by themselves are not studied object, and when you when you not very clear objects. I mean, very well studied objects. Although right now there are a lot more in them, right, than used to be before. Throwing away just part of the jet, which is a colorimetric part of the jet from neutral particles, it's kind of like not really improving the situation. Therefore, I think that the mainstream of the Atlas analysis is to do it with fully reconstructed jets with the colorimeter as well. So
okay.
I wouldn't be able to say more than that.
Okay.
I think
Yes.
I think it's just there are so many other beautiful things which Alice can do, and Atlas cannot. I was just showing you one example of that. but with jets, I think Atlas is in a better position.
Okay. Yeah. Thanks.
Okay, Victor.
Yeah. So if you can go back to slide 8 or 7, where you initially showed us why. Yeah, this one. Yeah. So I know this is very basic, probably things, but my question is related to this distribution. Like, so we assume that the measurements will almost always give us this bell-shaped distribution or Gaussian distribution. But when can we expect that some other distribution may arise, like it's not a Gaussian?
Well, I mean, the Gaussian is just a separate case because it has some justification in the central limit theorem.
Yeah.
If you're doing, for example, if your results here are based on some kind of low numbers, it could be Poisson distribution, of course, not Gaussian. Poissonian becomes Gaussian at large means, but it will be otherwise Poissonian.
Right.
I was not saying that. I was saying a slightly different thing. I was saying, unless you specify this, people would understand the convention like this. It's more like about the convention. I mean, in principle, you can say whatever you want in the paper. If you explain it, it's fine. But most people don't. And it's not like the worst case. It's a very clear. It's a relatively clear case. The bad thing starts, for example, when somebody defines the systematic uncertainty. Well, this is not systematic, but in another case, like the full corridor, right? And he says, for example, somewhere in the paper, it's written that this kind of systematic uncertainty is the full corridor, so the maximum to minimum deviation. Fine, but if you continue doing your analysis, in other place you will take it as the root mean square. How would you combine these two? You have to divide them by 3 or do what? It's this kind of problems, right?
Okay. Okay, thanks.
Again, if you write something, you can say whatever you believe is the best for your analysis.
Okay. I see Subhash has raised your hand. Subhash, you want to ask?
Yeah. So hi, Sasha. Thank you for this very nice comprehensive talk on the uncertainty. So I have one question on the thing that you mentioned about this correlation between the statistics and the systematic uncertainty. So is there a way we can measure it? For example, using this so-called I mean, there's a paper like Roger Barlow where people used to like take out the statistical error and like doing some kind of analysis in that. So do you have any thoughts on that?
Is there any particular slide you refer me to, or it's
I think in the summary slide somewhere you have mentioned that it is needed to measure the correlation between the
okay. So with statistical uncertainty, you cannot do anything, right? I mean, if you have less statistical uncertainty, the only recommendation is try to use it all. In most cases, it's to benefit, although there are in some cases more statistics doesn't help. If you have like very different measurement, for example, you measured something in 2015 and then you're trying to measure the same in 2022 and you have slightly different detector, then more statistics not necessarily help. What I was saying about more statistics is that, for example, think of a tug and prop method. If you allowed yourself to accumulate enough Z-bosons, you can recalibrate your tracking system with the scale factors and essentially improve the measurement of something else. This is what I meant. So more statistics helps you to handle systematics in a better way. Although, you know, that's basically was the idea. In other case, for example, in some of the analyses, we thought of, we have like a choice. What we would prefer, take the scale factors from the PP collisions, which are very well measured because of enormous statistics, or try to work out our own scale factors from lead-lead collisions, which may be different because these are lead-lead, but they would certainly have a much worse statistics because lead-lead collisions are much more limited in it. Sometimes you have to make a choice like that and not clear which way would essentially reduce the systematics better. But again, the goal is to bring the systematics down.
Okay, thank you. Yeah, I got your point.
Okay, there are more questions. So I have a question, Sasha. So you mentioned about this centrality determination we could do with ZDC as well. So how does the centrality determination from the ZDC compare with the other usual technique, I think mid-rapidity multiplicity, charge particle multiplicity?
First of all, I never said it. You cannot do centrality from the ZDC itself.
Oh, okay.
What I didn't say, well, I mean, I didn't say it. You can do it in certain cases. The problem with the 0-degree calorimeter is the following. I don't have a corresponding plot, unfortunately, but think of it this way. In the central collisions, the number of ZDC, so again, let me, I'm trying to explain the plot without, oops, sorry. I did this, no, that wasn't intentional. Give me a second. Where I was in, maybe sorry, I lost my presentation. That was unintentional, but let me. I don't know, something went wrong with my computer. I apologize for that. I'm sorry. I have to do something else here. Okay, sure. Okay, I hope I'm back, at least partially, right? Yeah. So the problem with the ZDC is the following. So if you would try to plot the ZDC, let's assume on this number of participants, you will have something like this. I'm trying to find actually something to draw with. I don't know. You will have something like this. Okay. It means that in this region, when the number of participants is close to 400, sorry, I went too aggressive to the right. To 400, the number of neutrons will be very clear what it will be. It will be total number of 422, right? Minus the number of participants, and taking with a ratio of neutrons to protons, because after all, ZDC is the counter for neutrons and protons, right?
Right.
But if you look in this region, it will be falling down. And here, what works against you is the fragmentation, because in the peripheral collisions, it's the question whether you break down the nuclei to the pieces. To actually measure the number of neutrons, you need to separate every neutron from the proton, right? In the central collisions, it's kind of given because you have so much energy that your spectator part essentially bursts into pieces. But in the peripheral collision, this is not guaranteed. In the peripheral collision, you may still have some rather significant large fragments which will keep flying inside the beam pipe. And they will never be measured in the 0-degree calorimeter because they have a charge attached to that, and they will be swapped away by the bending magnets. That's the problem, right? So basically, this is a counterintuitive behavior which essentially prevents you from doing any centrality in the peripheral collisions. You can only do it in the central collision. In a central collision, you can do it, but again, because it's a counter, you count a very small number of neutrons here, right? Sorry, I missed that too far, sort of moved that too far. This tip has to be actually here, okay? And here you will have like 20 neutrons. So your statistical significance will be square root of 20. That's also not so good. So you can try to do the neutron like an unbiased thing, but only in the central collision. In the central collisions, you are unbiased anyway, because you have so much activity coming from all soft interactions that who cares that you may have another jet there. But in the peripheral collisions, you will be basically swapped away by this other process, which actually works against you. So I don't think that the 0-degree calorimeter centrality, I saw it published in one of the papers, I think by Alice, but I think it was like a mere demonstration that, well, I didn't really remember what was the main message of using them. Really don't remember. But I don't think that this is so easy. What the 0-degree calorimeter really helps is to separate from photonucleon. Because if you have a neutron in the 0-degree calorimeter, most likely the proton which sent it underwent the hadronic interaction. It lost a neutron, right? I mean, and if you don't have a neutron in the 0-degree calorimeter, that's most likely was a photonucleon. That is the biggest part what the 0-degree calorimeter can give you. And this is extremely important in my view.
Okay, thank you. Any other questions we have for Sasha now? Rishi, shall we stop the recording and then have one more last
Sure.
call? Yeah. Okay. So last call for any